So my name is Prasanna Balaprakash. I'm a computer scientist here at Argonne. So we are planning to start the day with deep learning basics. So I'm pretty sure some of you are already doing machine learning. If that's the case, hang with me for this session. You will be exposed to a lot more interesting stuff throughout the day. But we will start from something very basic. Okay, so to begin, so what is difficult for a computer? So I want to make a survey. Is it predicting or saying that there is a cat in this picture or sending a rocket to Mars? How many of you think predicting cat in this picture is difficult for a computer? Please raise your hand. Okay, and how about the second one? Nothing. Okay, great. Yes, that's right. It's very difficult for a computer to say that this is a cat, whereas sending rocket to Mars, we have figured out the math and we can do that very well. Given the budget and all other things, we can still do that. So that's the reason why the task of identifying something that we do so well in natural world is so difficult for a computer. So the system that can do this really well is our brain, right? You can see that picture, you can see a couple of cats, and you can easily generalize to other cats and similar with other animals and so on and so forth, right? The system that can do this very well is brain. And brain is, fundamentally brain is made up of these special cells called neurons. And neurons, they were sort of connected to each other, and over the time, we sort of look at things. We know what those things are. We manage to identify what those objects are. We throughout our life we learn how to identify those patterns and put together those patterns and come up with what those objects are. So even if you think about intelligence, right? So at the basic level, we have neurons. Neurons are connected to other neurons, and eventually this gives rise to some remarkable things such as intelligence, right? So in order to build some system, that can recognize cat as a cat in this cat picture, so we looked at the machine learning. So the machine learning approach to recognize those type of pictures or identifying objects take inspiration from neuron itself. So this is something called Perceptron, and the history of Perceptron goes all the way back up to 1952. So if you see neurons are made up of dendrites, nucleus, cell body, and axon. So what happens is some neuron will pass signals through dendrites, and the neuron will get those signals, and then they pass it through axon, and the axon terminals are connected to other neurons. Okay, so if you look at Perceptron, that is this building block of artificial neural network, what you have is some inputs that come into some central computational unit, okay, and it performs some type of computation, and it gives that result to other artificial neurons. Okay, so this is the fundamental unit of artificial neural network, and this is again loosely inspired by neurobiology. So we use such units to build systems for supervised deep learning. So what is supervised deep learning is given set of inputs such as cats, dogs, horse, and so on and so forth, and outputs. The outputs are the labels, right? Labels that say, okay, so this is a cat, this is a dog, this is a horse. And we want to build a system that goes through this process called training. And this training gives us a model, okay? And using that model, we can then go and give a new image and ask what that image is and predict what that image is. Whether it as a cat or dog or so on and so forth. So this is one of the sort of a traditional or a common approach in machine learning, the supervised learning. And in the rest of the talk, we will be focusing on how to develop deep neural networks for this supervised learning. And we call this as supervised deep learning. Okay? So outline of the talk, we will first focus on, we will revisit perceptron more from mathematics and computer science perspective. And then we expand that to what we call as deep neural networks. And then we will focus on training deep neural networks, and finally, how to improve this training. Okay? So perceptron, so as we have seen previously, you get some inputs. So that's what you see here, x1, x2, x3, up to xn. And consider this as some constant. One is coming in and the constant b. So you always have this. And you have series of weights, W0, W1, W2, Wn, and each of these weights sort of combine with this particular input. Okay? And then what you have there is you sum them up, and then finally you give that as an output. So if you see this, right, the equation at the top, what you have is for I equal to 1 to n, right? So n is the number of inputs that comes into the perceptron, and you multiply that with weights wi. Right? That weight is specific to that particular input, and you just sum them, and you add this constant b, which is bias. Right? So if you look at this equation, this is something that you are already used to. If you're fitting linear models, some of basic calculus, basic regression type method. So this is nothing but a simple linear regression. Right? Okay? So this is what the perceptron will do. So there's one little thing that is different from linear regression is something called activation function, or something called this function g. You take that linear combination of inputs and pass it through this function g. Okay? This function is a nonlinear function. Okay? That makes perceptron a lot more powerful, and not as an individual unit, but if you put together many perceptrons along with this nonlinear activation function g, it has remarkable power to model nonlinear functions. And that's the base of all deep neural networks. Okay? So we'll look into what this function g is. And again, if you before getting into that, let's say let's formalize this. So we have the output that is a function of g, and that function g takes linear combination of inputs and add a bias term, where x is the number of inputs, x0 to xn, and w are the weights w0 to wn. Okay? So in the image example, x0 to xn are the pixel values. Okay? Or if you are dealing with some other problem, let's say you have a simulation and you want to predict the output of the simulation, the input to the simulation will be x0 to xn, and the output is the output of the simulation. Yes?
Why do you need the bias? Why is not enough with the weights?
You can do that with the weights alone, but usually you will have a bias to sort of so there are some functions, right, which can be modeled easily with bias by setting all the weights to 0. Okay, so you want to have that ability. Let's say you have a constant function, right? That constant function is easily modeled or better modeled using just simply bias. And if you have a training data that is a constant, then you should learn the weights as zeros and simply keep that. Okay. All right. So to give some concrete examples, so here is how you have some inputs and you multiply those inputs with those weights and you add the bias, and this is what you will have as an output. And so one commonly used activation function, right, so nonlinear activation function, is sigmoid activation function, and basically that sigmoid activation function is given by 1 divided by 1 plus e power that output, the linear combination, right? So let's say this linear combination is 3.2, and by simply substituting that value to this sigmoid nonlinear activation function, you get this value. Okay? So there are many different activation functions, and the right type of activation function depends on the type of the data, and that's something that you will be working on and trying to find out, okay, what is the right type of activation function for this particular data. Okay, so the one that we saw now is the sigmoid activation function. Okay, and there are several other activation functions such as tanh, ReLU, leaky ReLU, and there is a bunch of it. And practically you won't, in practice you don't really need to implement all these activation functions. These are available as part of some common deep learning packages, and you just call them as names like sigmoid, ReLU, and so on and so forth. So, but it is important to know what these activation functions are doing, and you use them appropriately. Okay, so in a nutshell, activation functions take an input or take a value, take a scalar, and sort of map that to some nonlinear functions, and that gives the power. That gives the power to neural networks to model highly nonlinear functions. Okay, so why we need nonlinear activation functions? So take for example, you have 3 different classes, right? So you have 3 different classes, and the data is distributed like this. If you don't have nonlinear activation function, then how many neurons you can put, or how many artificial neurons or perceptrons that you put into the network, the maximum you could do is just linear model, right? So you will have a linear separation like this, and which is not powerful to separate this data which is in the red, yellow, and blue, which is distributed like this. Once you introduce nonlinear activation function, what you will see is the neural network will be able to classify this data much more much more precisely than what a linear model could do. Okay, so the key or the power of neural network comes from this sort of nonlinear activation function. You can add millions of neurons, you can stack them, but if you don't have nonlinear activation function, you cannot model this. Okay, so let's for the further discussion, let's use this notation. Let's say if you have a perceptron like this, we will represent this. We just remove the bias, that it's already there, and we will represent this as the figure shown there. So multi-layered perceptron is simply, you have these inputs, and what we have seen so far is this set of inputs and one H01, right? And that gives the output. But now we can just take several of them and stack them up, right? So H1 is similar to H0, but will have different weights. H2 will be similar to what we have seen in the previous slide, but with a different set of weights. Okay? So each one of them have their own set of weights. And then this one, again, think of this as the same perceptron, right? Set of inputs, each one of this arc will have their own weights, and then you will have an output with an activation function. Okay, so this is multi-layered perceptron. And what we call deep neural network is simply a neural network with more than one hidden layer. So in the previous case, what we had is only one hidden layer. Now we have 2 hidden layers. Again, think of each unit as a set of inputs coming into that unit with their own weights, and this gives an output. And this one, the H52 receives input from all these units, combine them using their own weights, and then give the output. Each one of them pass through a nonlinear activation function. Yes?
What would be the difference between increasing the number of neurons and increasing the number of layers?
It depends. It depends on the type of the data and so on and so forth. So the state-of-the-art methods use a lot more depth. So in particular for image recognition task, what it turns out is, the lower level or the hidden layers that are close to the input sort of extracts patterns such as edges. Okay, and the next level take those edges and put together as shapes. You go to the next level, the shapes become more sort of objects, and finally the objects become, let's say, cat or dog or so on and so forth. So there is this hierarchical future representation that is extracted by neural network automatically. Given a lot of training data, it can adjust the weights in such a way that it put together these type of future representations and combine them in a hierarchical way. And that's where the power of neural network comes in. So that's why it's called deep neural networks. So mostly, if you use a lot more layers, you have this representation are extracting this hierarchical representation.
So increasing the number of neurons would just allow you to, let's say, have more shapes that you can detect.
Again, it depends on, so what I said is for image recognition data, right? So, yeah. So, again, you will use, but we also need to be careful, right? If you keep on increasing the number of layers, then the number of trainable parameters increases. So all the weights we need to train, right? We need to identify what are the right weights. So there is a careful way to put together all these things, and that's something that you will be seeing the rest of the day. Okay. Yes.
Just follow up on that. So if you were to relate this back to just doing a simple linear regression, would that, how would this image, what would be the equivalent of this image to just linear regression?
So linear regression is, let's take these inputs, only one unit, right? So all these inputs are taken with some weights, and one unit that combines, and then it doesn't have any nonlinear activation function. You just pass that scalar. That's it.
Would you have more than one layer though, because you have a lot of different types of inputs?
Okay. So if you don't use nonlinear activation function, it doesn't matter how many layers you stack, because a linear combination of a linear combination will be another linear combination. So you will eventually be capturing that with single linear combination. So yeah, that's it.
Thank you.
Yeah.
So what's the x-axis on the activation function?
Oh, okay. So let me go back. So the x-axis of the activation function is the scalar that you get. The scalar that you get from the linear combination of the inputs. Okay? And you take that and you pass it through that activation function, and what you get is this y-axis value. So, yeah, maybe I should have made it clear. That's fine. Okay. Okay. So right now we saw the high level structure, right? So deep neural network, there are weights and given the inputs, but we haven't talked anything about how to identify those weights, because identifying those weights means that you are modeling this underlying function very well. So that's the whole thing about training the deep neural nets. So again, we are looking at supervised deep learning, inputs, outputs, and it undergoes this, deep neural network undergoes this process called training. It produces a model, and from the model we can do the prediction. Okay, so training consists of 3 different phases. Okay, first one is forward pass. In the forward pass, what you do is you initialize the neural network. You don't know anything about the input and output and whatsoever, right? So you initialize this neural network with random weights, right? W1, W2, so all the weights of these arcs will be random. Okay, and what you'll do is take an image, let's say you take the cat image, and pass through this neural network. And as a prediction, what you will have is dog. So you will get a scalar, but then there is a way to convert scalar into a particular prediction, right? So if you are dealing with 2 classification, let's say cat and dog, and the output here will be some probability, and based on the probability, you can say whether it is a cat or a dog. Okay. So what you have initially is you take this neural network and then pass this cat image and see what the result is. And because it's a random weight, right, it will predict this as a dog. Now, the backward pass is one in which you want to go and tune those weights. Right? So you initialize all those weights random. Now you want to go back and tell the neural network, okay, you have made a mistake. Instead of predicting a cat as a cat, because this is during the training process, right? So you know this is a cat. you go back and say, and you go back and want to sort of fine tune the parameters of the neural network, the weights of the neural network in such a way that it corrects its prediction. Okay? So you know what cat is, you go back and sort of fine tune all the weights of the neural network to say that is a cat. And how you do that, so you have something, you have to first quantify the error, right? So instead of you have a cat and you predicted that as a dog, now you have to quantify this error. And the way that if you look at quantifying the error is something called objective function or loss function. So the loss function is nothing but you have network parameters theta at that current state, right? So the thetas is set of all trainable parameters of the network. And what you have here is f of xi is the ith training data. Okay, xi is the ith training instance, that is a cat image, and you have predicted that as a dog. So f of xi of theta means that you passed that cat image and predicted some value, and that predicted value is dog, but observed value is cat. The observed value is yi. Okay? So the loss function basically takes the predicted value and observed value and computes some measure. Okay? So we can say that, okay, cat is not a dog and my error is 100%, right? When cat equal to dog, my error is 0%, right? But that, mathematically, that is a very hard problem to go back and tune the parameters of the neural network. So you come up with some function that allows you to sort of help the underlying optimization algorithm that goes and tunes those parameters. We'll look into that. Okay. So if you have to generalize this, what you do is you have n training instances, right? And where I equal to 1 to n, and you compute that loss function over n training instances. So you don't do tuning the parameters using one example, but you take a bunch of examples and you pass it through the network, compute the error, and then go back and tune the parameters of the network. Okay? Yeah?
Is there only one set of weights that would minimize the loss?
No, so we have, there's only one set of weights, right? The set of weights is set of all W's in the network.
Oh,
okay.
Like the values of the weights, is there only one set of values for those that it's going to minimize the loss? Or maybe I'm misunderstanding.
So let's say your weights of the network are W1 to Wm. Okay, that represents set of all weights in the network. Set of if you have 1,000 edges that connects in, right? Then you have 1,000 weights to optimize.
But I think he's asking about the uniqueness of the weight.
Yeah.
Oh, uniqueness? No, each weight can take. It's a real parameter, so it can take any value.
There's a global optimization problem. You have
Do you have
like
only one
minimum.
vector that minimize this function, or can it be like a combination, or?
Yes.
Oh, okay. So it is. You can think of this as one vector, but this vector is really a large vector. So especially if your network is, you will eventually deal with million parameter optimization. So your vector is 1,000,000 entries.
Is it the only one?
Yeah, is it the only one?
Is there
Is there a singular solution?
Oh, okay. So there is no single solution. We'll come into that. Okay. So it's a very difficult nonlinear optimization problem, and usually it's very hard to find a unique solution for that.
Okay.
Sorry about that. Okay. Thanks for the clarification. Cool. Okay. So one example. So this is something called cross entropy loss. When you're dealing with classification problem, as I said, cat versus dog. Even if you are like very close in terms of probability, let's say you are with a probability of 0.49, you predicted that as a cat, but you want to give incentive to the network instead of that probability of 0.1, right? So what you have is something called categorical cross entropy. So forget this formula. What it actually means is, if you say the true label is 1, let's say it's a cat, and if your network predicts that with a probability of 1.0, then your loss will be 0. Okay? But if it predicts that with probability of 0.8, you still have a little bit of loss, right? So the loss function, you want to still minimize. Whereas if your predicted probability is 0, whereas your true label is 1, then you want to have a high loss. So basically the categorical cross entropy takes this two categorical variable comparison and make it as a sort of a nice loss function. So using that loss function, now the optimizer, the underlying optimizer, can go and fine-tune the parameters, right? So if you are in this region, you have to sort of you don't drastically change your network weights. Whereas if you are in this region, you will go and change the network weight much more strongly compared to this region. So that's the idea. So this gives network the ability to to change the parameters with respect to how well it is doing. Okay. So this is if you had to represent the whole thing. So this is an argument. So basically we have to minimize this loss function, right? So given n training data, we have to train the neural network in such a way that this loss function is minimized, and we can represent that the whole loss function as j of theta, where theta is equal to w1 to wn. So that's the weight vector of the neural network, right? And the whole point of training is how to minimize this objective function or this loss function. Okay. So coming back, so this is also another question. So there is, so this is a simple example of the neural network loss function. So how the loss function looks like with respect to parameters, the tunable parameters. And often this surface is very nonlinear. It has a lot of local solutions. So local solutions in the sense, let's say if this is the surface that you are optimizing, okay? The local solutions are those that are not actually optimal. And this is the global solution, which is the optimal for this surface, okay? So this is really a continuous surface. This has nothing sort of, in reality, this is, you can see this as like a 3 parameters, right? But in reality, you will be dealing with 100,000 parameters or a million parameters. And think about the surface. Surface is really complex. It's, first of all, it's nonlinear and discontinuous sometimes. And finding the global solution for this objective function or for this loss function is very hard. So that's why you don't use or you don't run the training up to optimality and things like that. And even in those cases, it's very hard to prove optimality. Okay, so these are. So to give an analogy, so how we usually do that is we use something called gradient descent. Gradient descent is the underlying optimization algorithm. So there is a separate session this afternoon that talks about optimization in machine learning and in particular deep learning. So what are the underlying optimization algorithms that were used to optimize those parameters? So to give an analogy of this, what you usually hear, in sort of training, what you do is, usually you start from somewhere there. So with the random weights, you are on the top of the hill, and you want to go here, right? So that's where the water is, and the point is, you have to do that blindfolded, because you don't know the surface, and all you can do is to take some step and see whether you are minimizing it or not, right? You are minimizing, or you are taking steps towards your goal. Okay. So the algorithm to do that at a high level for the gradient descent is you start from the current coordinate, and then you just see see your neighbor, whether you have some sort of slope, then you take a step towards that slope. Okay. So, and coming back to the training, right? So in practice, all the deep learning frameworks such as TensorFlow and PyTorch already provides different type of optimizers and different type of loss functions and things like that. So usually you don't code these things by yourself unless until you want to build things from scratch and try to understand what's really happening, you won't do that. So whatever we saw in terms of loss function and in terms of optimization, it's just one line of code in TensorFlow and PyTorch. You call, you build a model and then you go and say model.fit in the bracket optimizer equal to SGD. That's it. You don't need to do any optimization by yourself. Everything is built for you, and usually that's the mode of model training that you will be looking at. So what is challenging here is often you will build a model on a particular data set, and then what you will find out is, my model is not training well. My model is not fitting for the current data. Often you have to spend your time in improving the training process, or how to make the neural network learn the underlying function or for the given data. So we'll look at some of these things, and most often you will be spending time on this part of training process. Okay, so the common thing is, in particular when it comes for neural network, you have this idea of underfitting and overfitting. So underfitting is something that your underlying function is complex, but the model that you built is not powerful enough. Okay, so this goes back to using more layers of the network, layers in the network, or using right activation function and so on and so forth. But underfitting is a concept that your underlying data is a lot more complex, but the model that you fit is not good. Okay, overfitting is something where your model is overly complicated, and what happens is that the model starts learning to model noise in the data. Okay, so consequently, what happens is your model is so sophisticated that even it sort of starts looking at smaller differences in the data and tries to model them. And what happens because of that? In the training data, you will have a fantastic accuracy, but once you take that model and go and try it on the testing data, the model hasn't seen during the training process, your accuracy will be very low. So the key here is to sort of balance this overfitting and underfitting and try to have a model that is in between. And that model will be a lot more generalizable, have higher predictive power, and can perform very well on the testing data. Okay. So there are many ways to address these two problems, but the point to be noted is you fit the model, everything is given for you, like optimizer is given, activation functions are given, even building a model takes 5 lines of code in TensorFlow or in PyTorch. But when it comes for applying these type of methods to your data, to the type of data that you are dealing with, or the scientific data, often we are in this process, underfitting and overfitting, and we have to find out what is the right network, what is the right type of parameters, what is the right type of activation functions for this given data. Okay. So how to avoid underfitting? Okay, so this is again going back to increasing the capacity of the network, right? So if the network is not powerful, you are not going to do very good on the training data itself. So go and increase the number of units per layer or number of hidden layers. So that's the first thing to look at. And more importantly, use appropriate type of network. So if you're dealing with images, don't use a fully connected neural net. Images are better handled by something called convolutional neural net. If you're dealing with sequence data, use some sort of recurrent neural network, or there are state-of-the-art algorithms such as attention and so on and so forth. So figure out what is the right type of network for the particular type of data that you are working. Even if you identify the right network, let's say images. So there are a lot of network available built by Google for classifying images, cat versus dog. But if you take those network and try to apply to, let's say, scientific data, such as cosmological data, identifying stars versus black holes, you might not see good performance because the model that is built for identifying cat versus dog is different from the model that you will use for particular modality in your scientific data. So what you have to do is, it's okay to start with a convolutional neural network which is built for images, but then you have to go and identify and sort of fine-tune the parameters of the network and adapt it for the data that you are dealing with. So some of them experiment with hyperparameters such as activation functions, optimizers, and batch size, and so on and so forth. So there will be one session later this afternoon dealing with how to do this automatically. How to avoid overfitting. So this overfitting will be, if you have to see, underfitting versus overfitting, overfitting is a big problem because in neural network you can build a really big network, right, with millions of parameters. But you have to make sure that this is not overcapacitated. It's not going and trying to find and fitting the noises in the data. So to give, so this is something that I found online where Enrico Fermi, once a scientist back then said, like, he modeled the physical phenomena, and Enrico Fermi asked how many parameters he used to model that physical phenomena. He said like 4 or 5, and then said with 4 parameters I can fit an elephant. With 5 I can make his trunk wiggle. Actually, some physicists later went out in 2010 and fit an elephant with 4 complex parameters, and that was fun. So take that scenario and compare to the current neural network literature. So we are dealing with millions, and people are talking about billions, and OpenAI is going even bigger to say, like, if we have to build artificial general intelligence, then we have to build even bigger network. So we are building a lot more bigger network with billions of parameters, and overfitting is a problem. And okay, if you're dealing with application that has a lot of data, this is okay, somewhat. But if you don't have a lot of data, then overfitting is a problem, right? So if you don't have a lot of data, going for that many parameters, your network will be overcapacitated, and you will not be able to extract good performance out of it. The other way to address this problem is, if you have only few data, right? Yes?
So can you be more specific when you say a lot of data or a little data?
If you have a lot of data, then you can build a lot of bigger network.
So like, what is the scale of a lot of data? Is that 10 images? Is that 1,000 images? Is that 1,000,000 images? Right?
Okay. So there is, in terms of this billion parameter network, right? So we are talking about billions and billions of data records. So one way to think about, right? One way to think about networks and network parameters is, your network is a compressed representation of your data. If you have 10 data, like 10 data points, building a 1,000,000 parameter network is overkill, right? Why you need 1,000,000 parameter? We can talk about, why my single data point is billion pixels. In that case, go and build a bigger network. But one way to think about it is, neural network is one way or the other. It's a representation of your data. How to represent your data in that functional format. So if you have 10 small images, going for 1,000,000 parameters is probably overkill. Okay. So again, it's really data dependent, and one need to experiment. But always think about this: how many data points I have, how my data is represented, and how many floating points I need to represent that. And your network should be a function of that. Okay. So the other point is, if you have only 10 data points, what you can do is, for some type of data, you can do data augmentation. You can take one particular image, rotate it, or you take a patch of it, and so on and so forth. This is all cat images, but if you have only 10 cat images, you can generate hundreds of cat images by doing rotations, translations, and sort of different type of transformations on this one particular image, and get more data out of it. Yes?
If you were to relate this to maybe some set of like physics-based data, would that mean like, oh, you could take the derivative of this data and that might be considered data augmentation as well?
Exactly.
Okay.
Derivative not in the mathematical sense, but some derivative of that particular image. Or
Could you say I have data and I know that this data has some, I know I can infer stuff from doing this mathematically to my data. So that's another layer, or that's another set of data, or and that's not considered data augmentation?
No, that is a data augmentation. That you can use that information to generate more data, right? So Corey is going to talk about something called generative networks. That's an interesting concept with the deep neural net, where we start from smaller data and then teach a network what is the underlying distribution of that data generation process and sample more from that distribution. So that's a very interesting concept that is sort of what you are saying. There you are doing this manually, but there are ways to teach a neural network how to do this automatically as well. But if you know something about the underlying domain, and if you can derive more information from this particular image and do a data augmentation, it's better. So generally, if you can generate more data for the training, it's better. So dropout is another concept where during the training process, what we do is we randomly switch off some of the units in the network per layer. So what it help, so this can help to sort of address the problem of overfitting, because you are not using all the units, and at the same time, by randomly switching off the units, but in different passes of the forward and backward passes, what you have is you are forcing the network to learn the underlying function, but using only part of the network, right? So in one pass, you will use this part. In another pass, you will use a subset of it. In another pass, you will use another subset of it, right? So this gives the ability to model the underlying function, but only a subset of neurons will be used for that training purpose. Okay, so you are not using all the parameters. So the other approach is to use early stopping. So let's take you take the training data and then split some of the data for the validation, and then what you will see is you train the network, and so this is the number of iterations for the training, and what you will see is after some time the network will start learning the noises in the data, and your training performance goes up and up because you start overfitting, whereas your testing accuracy drops off. So one way to catch this is take some data, don't give that for the training, and while you are training, test the network on that data, and then once you reach this cutoff point and you start seeing that the network performance is sort of dropping on the unseen data, you stop the training. So early stopping is is an approach that we use much more frequently to do this. And another approach is to use regularization. Here, what you will do is in addition to this loss function, this is the usual loss that you use for the training. You add one more term with some parameter lambda, and that basically this term forces your neural network parameters close to 0. If it is not someone is asking? Okay. If it is not 0, then your loss function value goes up, right? So because using this regularization term forces, in addition to training, right, in addition to finding the right networks, it forces the network weights close to 0, which makes several of the trainable parameters to 0 and addresses the overfitting problem. Okay, so we're pretty close. So as a summary, so first we saw what a perceptron. Simply, it's a linear combination of the inputs, adding a bias and passing it through a nonlinear activation function, and then you stack them up to form a neural network, single layer, and from that you just keep on increasing the layer. You can form deep neural networks, and the training process is composed of 3 phases: forward pass, backward pass, and identifying the loss function. So once you identify the loss function, then it's pretty straightforward to train a neural network. But most often, what you will be working on is how to address the problem of overfitting and underfitting. There are different approaches to that, and the correct approach depends on particular data set. And often you will be using a combination of these approaches to address the problem of overfitting and underfitting. With that, I will end my talk, and I will open for questions. Thank you. Yes.
When you're doing gradient descent, if as a loss function you use the cross entropy, can't it be a problem in terms of how big a step you give if in the logarithm you have a value that is very close to 0?
Can you repeat the question?
If randomly by chance in the loss function that you use as the cross entropy,
Yeah.
the x is very close to 0, and then the log becomes very big, and then the step becomes very big, and in the gradient descent you give too big of a step.
Yeah. So this is something that that will become a problem. So there are two problems called exploding gradient and vanishing gradient problem. So what you are talking about is an exploding gradient problem where your gradients become too big. So because of the loss function value that you just mentioned, and there are ways to address that. So you will use normalizations and other approaches to make sure that your gradient value is not so big, and you clip that, right? So you clip the gradient value. It should not be more than some particular value. So yes. So during the training, what you will see is when there is a gradient exploding gradient value, exploding gradient problem, then your loss function will become nan, and all your weights will become garbage, and you can identify that during your training process. So that's where the gradient clipping, gradient norm approaches that you will use as a part of the training process will address this problem. Yes?
How do you initialize your network? So I assume if you say constantly everywhere, all the neurons would want to do the same thing in that gradient. So.
Yeah. So there are many different ways to initialize. So one is random, or you can use some distribution to initialize, and there are different inbuilt approaches. If you are using TensorFlow and PyTorch, there are different ways. You don't even need to do that by code. You just call one function, and that will initialize the neural network in a particular way. And in fact, if you think about it, the initialization plays a crucial role, right? It determines where you start from, and sometimes finding the right initialization is also a key. And you can use that as a hyperparameter and sort of experiment with what is the right type of initialization that I need to use for this particular data. Another thing that we do is something called transfer learning, which means that you have a network, okay. Let's say you can, if you are dealing with convolutional neural network, what you do is go and get the weights from a network which is already trained on some images. Okay, use that as a starting point. You can take those weights and initialize the network with those weights, and you are, for several problems, if these two problems are related, then you are starting with a very good starting point, right? So you can also use that.
Yeah, just building on his question. So starting with different initialization may lead to different weights for parameters, right?
Yes.
So do we need to do actually multiple training and then average the weights, or it doesn't matter basically?
So neural network training is very expensive. We cannot afford to train 1,000 different initial starting points and try to combine the weights. Although there are some approaches to do that if you have enough resources. Usually what we do is we start from a particular point, and if you remember the type of objective function or the optimization function that we are trying to optimize, it's highly nonlinear, and finding a global solution is hard. So depending on the type of initialization that you use, you will end up with the different local solutions. The cool thing about neural network is, or at least this type of objective function, is that there are several good local solutions, and it's okay to get into a local solution, But as long as the performance is okay, then it's fine. So you don't strive to get the global solution. In fact, finding global solution is impossible if you're dealing with million parameters. Yes?
So for the binary classification problem that you showed us, essentially if you're talking about the input layer as sending in pixels,
Yeah.
and the output layer will turn out to be, say, like a two-layer probability function, either 1 or 0. So I'm just wondering if there is a sanity check type of functions that can be incorporated to prevent the network from identifying any other garbage image. Say, if I pass in an elephant image, it's still going to have a probability of, say, a higher probability, and it's confident about it being a cat. So is there a sanity check to prevent that?
Yeah. So you can do that with the training process, right? So let's say you are dealing with only 2 classes, but take a random image, right? Generate a random image, and instead of dealing with 2 classes, do it as a 3 classes: cat, dog, unknown. Okay. Make sure that when you do the training, you put the cat image, dog image, and some garbage image, and that garbage image could be anything. So we are training the network to make sure that cat should be classified as cat, dog should be classified as dog, and all others should be unknown. So if it classifies this garbage image as unknown or a horse image as an unknown, then you get good points, right? So you have a loss function that sort of incentivize the network to put that into an unknown class, right? So in that way, you can make this work with an unknown image.
And so that can be extrapolated for any n images. Like for
Yes.
n images, you can do it for n+1.
So because you are doing unknown, right? So cat, as long as it's not cat and dog, the network puts that into an unknown, and that's how you train that, right? So you can do that. Great. Yes.
I just had more of a broader question. So I think for a lot of us who have not necessarily been trained initially in things like machine learning and data science, there's a lot of hype surrounding it, and it seems sometimes it's like advertised as this holy grail of solving all of our problems that are still open. And the tools look really exciting and useful, but I guess I'm wondering if you could maybe give us like a balanced perspective on how we can think about how this would be useful to our work, but not necessarily like in an overhyped way. Or like how do we communicate that without like falling into the cliche of, oh, this is AI and it's solving everything, and we as communicating our work and also thinking about our work with this as a balance. I'm just wondering if you have like some thoughts or perspectives you can give us.
Okay, so that's a tough question. So what we usually do, first and foremost, we need to understand what the underlying problem is, and is it really amenable for machine learning? Let's say if you have a pretty good physical model that can do a better prediction, then what is the point in doing machine learning? So that's the first thing. And the second thing, even within machine learning, as you said, there are a lot of hype, and we are trying to understand what type of methods are better suited for this particular data. And in fact, deep learning, we choose deep learning because we thought of like, given one day, if you have to choose one particular method and sort of train you all, we thought of going for deep learning. But there exist several other methods, and they are a lot more easier to train. To give you an example, gradient boosting methods and random forest, they do really well on several data sets. So what we usually do, at least from science perspective, we want to have sort of a thorough understanding of what type of method, it's a regression problem, classification problem. We start from some basic methods and understand what is the difficulty of solving this problem using basic method. Start from linear regression, right? And then slowly increase the complexity of the learning method and see if you have an improvement. If the linear regression already gets you, 98% accuracy, going for deep learning is an overkill. On the other hand, if you are dealing with images, with pixels, that's where deep learning methods will start doing better. Because think about the problem where you have to extract features in a hierarchical way, and you have to put together those features, and that eventually gives you a better classification. So there are class of problems that are better suited for deep learning, and there are class of problems that are better suited for different methods. And it's very important to understand, at least from scientific perspective, what type of method is better suited for what type of data sets. So communicating that instead of all going for deep learning, I think that sort of reduces the hype factor and take a look at the problem more from a methodological perspective, and then a lot of ablation studies and try to understand what type of components are responsible for what performance improvement. So that's another thing that we do thoroughly. There is a lot of hype, and we have to sort of make sure that we don't jump into deep learning because it's hyped so well. It's very important to understand the underlying principles of regression, understanding overfitting, underfitting, and generalization is the key. So when we make sure that we take the method and demonstrate it on a data set that this learning method hasn't seen. Being systematic and being thorough with the type of empirical studies in machine learning, I think that is key. And some of the issues also goes back to interpretation. And you will be Elise will be talking next about uncertainty quantification, which is very important in scientific setting. If you are talking about a prediction, you want to know the uncertainty associated with the prediction, right? So this is not so common in a commercial setting, but this is a lot more important in scientific settings. So again, giving a prediction with an uncertainty estimate for this prediction is very critical when we are communicating this to domain scientists. And there is also interpretation associated with it. So as long as you have, because deep learning models are sort of criticized for being black box and things like that. So making a model, taking a particular model and giving why this model is predicting something this way. Is it aligning with the physical models? Is it conserving the laws of this particular domain, conservation of mass, conservation of energy, and so on and so forth. So these are all the new exciting research topics that we are working on in scientific machine learning. All these things will eventually help us to address the problem of hype, I would say.
Do you think there's a lot of acceptance of studies that are really critical? Like, oh, I worked on this deep learning just to see if it worked better than my. I mean, is that there right now, or do you think that that's kind of a push that the AI or machine learning community is trying to have more of?
No, there are a lot of success. Even within Argonne and within DOE complex, there are several demonstrations of the use of machine learning and the success of machine learning.
Non-success of it.
Yes, there is also non-success. So that's a thing that we are trying to sort of understand where this will work and where this will not work, and how to make this work. So these are different aspects that we are working on. So, great, thank you. Yes.
So if you say you have some image that you've got an inference for, right? How do you know that image is within the range that your neural net is actually fitting, right? So the neural net is fitting some training set data, right? How do you know that whatever you're feeding in to get an inference from is actually within that range?
So that goes back to the generalization problem, right? So the underlying assumption in at least in supervised learning is that your training data and your test data comes from the same distribution. Okay, if it is a different distribution, then we have to think about how to adapt this method for this new data and so on and so forth. But if you take a vanilla supervised learning method, right, whether it's a deep learning or any other type of supervised learning method, the fundamental assumption is that your training data and the test data comes from similar distribution. Okay, so in terms of images, let's say you have 10 different class of images. Now you are talking about, okay, now I want to have a different set of images. Will that work? There is no guarantee, because first of all, it will take the different class image and put it into one of those 10 classes. If you want to be careful about that problem, you need to train that with an unknown class, right? So you have a 10 class and then put any type of garbage image into it, or any type of of animal image into it, which does not belong to these 10 classes, and have a class, something called unknown class. So that the network will be able to tell that, you know, doesn't belong to these 10 classes, but it belongs to the 11th class. Or the next session will be on uncertainty quantification, and that's where you can use the uncertainty estimate to say that, you know, this, you know, I'm predicting this, but I'm not confident about it, because I'm not confident because I haven't seen such images in my training data. So uncertainty quantification becomes crucial there. So there are many different ways to address this problem. So depends on what you exactly want from the method. Okay, great. Yeah, we will take this offline. I will be here whole day, so we'll talk later. Great. Thank you.